Hello, my name is Robert, and today I'm going to tell you about exponential separations between learning with and without quantum memory. This is a joint work with Sitan, Chen, Jordan Cotler, and Jerry Lee. One of the central goals of many scientific disciplines is to learn how the physical world operates. Here we consider learning as a combination of receiving, processing, and storing information, such as subsequently one could use the stored information to make prediction about the physical world. In conventional experiments that scientists currently do in the lab, one receives, process, and store classical information. The classical information is received by performing physical measurement on the physical systems, which is then processed using classical computer and stored in classical memory. However, as quantum technology starts to advance, we could imagine what future experiments could be like. Instead of receiving and processing and storing classical information, one could imagine having a quantum agent that could receive, process, and store quantum information. The quantum information is obtained by using quantum sensor, which is then processed with quantum computer and finally be stored in quantum memory. Given these dichotomy between classical agent that could obtain classical information, manipulate them, and storing them, and also quantum agent that could obtain, store, and process quantum information, a very important question is to understand what are the advantages of a quantum agent over a classical agent in learning about physical system and physical dynamics. In this talk, in this work, we provide some concrete answer towards this question. The talk will be separated into two parts. The first main part focuses on learning about physical systems, which would then be generalized to learning about physical dynamics in the second part. So let us begin with the first part of the talk. We will begin by defining the mathematical framework for learning about an unknown physical system, which is represented by a density matrix rho that is exponentially large. Particularly, we will focus on qubit system where rho could be represented by a 2 to the n by 2 to the n Hermitian matrix. And we consider a physical source that could generate a single copy of rho at a time. Similar framework has also been considered in Chen Li in FOCS 2020, also Huang, Kuhn, Presco in PRL 2021, as well as Haronov, Cotler, and Chi, also from 2021. In this framework, we will first consider the definition for conventional experiments, which is also referred to as algorithm without quantum memory in this work. So for conventional experiments, we have a classical agent running a classical algorithm that could perform some POV measurement on the physical system rho to obtain classical data. After obtaining the classical data, it will be stored in a classical memory. Then the classical data will be processed through classical computation to select the next measurement. For example, in the first experiments, one might want to measure certain properties. In the next experiments, given those properties, one might want to change the measurement basis in order to measure different properties, etc. So now after selecting the next experiments, the classical agent would just perform the measurement, obtain classical data, store the classical data, process it again, and then repeat. So after multiple rounds of experiments, where for each experiment, one copy of rho is being measured, at the end, there will be a classical memory that stores all data, classical data from all POV measurement. One would then use classical computer to process all of these classical data to make prediction about this physical system rho. On the other hand, for quantum enhanced experiments, which is modeled by a quantum agent, or also referred to as algorithm with quantum memory in this work, we have a quantum agent that could utilize quantum sensors to directly transduce this quantum state rho into its quantum memory. In the next experiment, the quantum agent will again use quantum sensor to transduce this into quantum memory and repeat. So at the end, it would have a quantum memory that stores all copies of this unknown state rho. One would then use quantum computers to process these quantum data and to make prediction about this physical system rho. So here is a more succinct description between classical agent and quantum agent, or also referred to as algorithm without quantum memory and algorithm with quantum memory. So as one could see, for classical agent, it only has classical memory, that is without any quantum memory. So whenever it wants to obtain data about this physical system rho, it has to perform some measurement. So we perform some POV measurement to get classical data. And then at the end, a classical processing is performed on these classical data. On the other hand, for algorithm with quantum memory, that is quantum agent, it has quantum memory that could store multiple copies of this unknown state rho in its quantum memory, which can then be used to perform quantum data processing followed by measurement. So as one could see, the main difference between the two is whether one has a quantum memory for entangling quantum information from past and future experiments. But of course, having quantum memory itself is certainly not enough. One would also require the ability to have quantum sensor to obtain the quantum data in the first place that will be stored in quantum memory, as well as quantum computer to just do quantum data processing. However, the main difference between the two is whether there's this availability of quantum memory for getting multiple copies of rho into there, where different copies is obtained from different experiments. We can then analyze the possible protocols and algorithms to study their learning ability and to prove separation between these two classes of algorithms. So now let us begin with the first task. So in this task, we are given an unknown n-qubit quantum system rho. The algorithm will learn about rho through the framework defined before, either with or without quantum memory. And after learning, we will ask the algorithm for the expectation values of observables from a collection of m different observables. In particular, we'll consider the case where these observables may not be compatible with one another. So recall that in quantum mechanics, compatible observables means they simultaneously commute with one another. And now the goal is to use the smallest sample complexity to answer these questions correctly. That is, to be able to predict the expectation values of all observables from this collection. This task is also known as shadow tomography from a previous work proposed by Scott Aronson. In particular, in this work, we proved the following theorem. We showed that to predict m observables in an unknown quantum system, learning algorithm with quantum memory requires n log m squared samples, but all learning algorithms without quantum memory need minimum of m and 2 to the n samples. We do note that this upper bound is already established. The main technical contribution of this work is in establishing the lower bound on minimum m and 2 to the n. We note that this lower bound of minimum m 2 to the n matches the upper bound for learning algorithm without quantum memory proposed in HKP20 up to a log factor. In particular, achieving m samples is very easy. Basically, one just measure these different observables on different copy, and then one would have that scaling. However, when m is much greater than 2 to the n, one could utilize a technique called classical shadow tomography in order to achieve a 2 to the n scaling for general observables. And furthermore, this theorem resolves an open question in Aronson and Rothbaum's previous papers. Basically, the question is that whether learning algorithm without quantum memory could achieve a similar sample complexity as learning algorithm with quantum memory. It would be great if it can, since learning algorithm without quantum memory is pretty much currently available. However, as the theorem shows, there's a significant advantage in using learning algorithm with quantum memory, such a lucky thing can never be achieved. We can also prove a similar theorem under a specific set of observables called the Pauli observables. So Pauli observables are observables that can be given as the tensor product of the Pauli matrices, that is I, X, Y, or Z. These kind of observables are very important in quantum mechanics and quantum computing, as well as in quantum chemistry, etc. And again, the goal in this task is to use the smallest sample complexity to be able to predict the expectation values of all of these Pauli observables, which has a total of 4 to the n of them. In this paper, we showed that to predict Pauli observables in an unknown quantum system, learning algorithm with quantum memory only requires a linear number of samples, but all learning algorithms without quantum memory requires at least 2 to the n samples. Again, this upper bound is established by me, Richard Kuhn, John Praskill's previous work, and the main technical contribution of this work is in establishing this lower bound for learning algorithm without quantum memory. So now in order to better understand this theorem, we would like to provide some proof sketch for how one proves this result. In particular, to illustrate why there is such a significant advantage for using quantum memory. The proof sketch would focus on proving the lower bound for classical agent, that is algorithm without quantum memory. And for the upper bound, we referred the viewers to this paper for the quantum upper bound. In particular, the first step of the proof is to consider a graphical representation for the memory state of the classical agent. In particular, we would start by considering the root R to be the initial state of the memory for the classical algorithm. And after each experiment, it would transition into different state. So for example, after first experiments, depending on the outcome, the memory state could become this node, or this node. And after the second experiments, it would go on. Well, generally, the graphical representation of the memory state could be an arbitrary directed graph. We note that when two nodes would be mapped into the same node after some outcome, it means some information is lost, because when you're in C, you wouldn't be able to know whether you come from A or B. So in order to consider the optimal protocol, the optimal classical algorithm, one can restrict ourselves to considering this graphical representation to be a tree representation. Now, depending on what the underlying state is, the transition probability on the tree representation will be different. So for example, if the underlying state is row A, then it might be more likely that in the first experiment, in the first measurement, one would transition into this node more likely than the two other nodes. On the other hand, for row B, the three transitions have the same probability. Now what we're going to do is we're going to reduce the prediction task, which is to estimate the expectation value of Pauli observable to some constant error to a many versus one distinguishing task. That is, we would like to distinguish between a null hypothesis, which is said to be the maximum mixed state, or one of the alternatives. So for each alternative, it's either I plus 0.95 PA or I minus 0.95 PA, or I plus 0.95 PB, I minus 0.95 PB, and more. So essentially, what we're going to consider here is that these Pauli observables, P, PA, PB, or PC, and so on, is selected from one of these set randomly. And basically, it's not hard to show that if one could achieve the prediction task, that is to estimate these expectation value to a constant error for all P, then one would be able to successfully distinguish between the null hypothesis and the alternative hypothesis. The reason is that for null hypothesis, for all P in this set, the expectation value would be equal to 0 because P Pauli matrices has a trace of 0 when we exclude these identity part. On the other hand, for these kind of states, one could see that there exists one of the Pauli observable P such that the expectation value is equal to either 0.95 or negative 0.95. Hence, if one could find, hence one could reduce the prediction task to this distinguishing task. And now one could use very basic information theoretic bounds to show that if one could succeed in the many versus one distinguishing task, then it applies a lower bound on the total variation distance in the probability over leaf nodes. So recall that the probability distribution over leaf nodes is essentially the distribution over the final memory state. So in order to distinguish between two hypotheses, the null hypothesis or the alternative hypothesis, one can show that using basic Lacombe two-point method, the total variation distance must be sufficiently large. In particular, it's the total variation distance between the naive node when the underlying state is the maximum mixed state or the average of all these alternatives. And then what we would do is we will then upper bound the total variation distance with a function of the number of experiments, equivalently number of samples. In order to upper bound the total variation distance, we will employ two different general techniques. The first technique is what we call an edge-based analysis. That is basically the intuition is that for every transition, every edge, which corresponds to a particular measurement outcome, we would like to show that the probability of transitioning in that path is very similar across different physical systems. In such a case, edge-based would work properly in providing a good lower bound and actually a good upper bound of total variation. On the other hand, if for some specific physical system, it's much greater, then the edge-based analysis could potentially fail. In particular, for predicting these observables, we would employ these edge-based analysis. Particularly, we would consider the transition probability, that is the probability of taking this edge when it's the null hypothesis versus when it's some alternative. In this setting, we can show that a strong form of uncertainty principle coming from the fact that Pauli observables are highly incompatible to one another implies that this quantity is very small. And this is the central quantity that we employed in the edge-based analysis. That is the probability, transition probability difference between the null hypothesis and the alternatives are sufficiently small. In some other technique, in some other task, we would also employ a path-based analysis when the edge-based analysis fails. The key ingredient in the path-based analysis is that the higher moment of the physical system has to be known. That is, one has to be able to analytically obtain the expression for, let's say, rho to some tensor power t, taking expectation value over the unknown state rho. If that could be computed easily, then one could employ a path-based analysis, which is a combination of tensor analysis and these random and these higher moments. On the other hand, if one is unable to obtain a succinct expression for the higher moments, then it is not easy to apply the path-based analysis. Utilizing this technique, we can establish this theorem in showing that in order to predict Pauli observables, all learning algorithms without quantum memory will require 2 to the n samples. Furthermore, one could also establish a lower bound of 2 to the n minus k over 3 for algorithm with only k qubit memory. Similar technique and also employs to establishing exponential separation for other tasks, such as testing purity of a state. In this task, the algorithm tried to determine if the underlying state is pure or is equal to maximum mixed state. And here we have a separation of a constant for learning algorithm with quantum memory and exponential for learning algorithm without quantum memory. That concludes the discussion of the first part. The second part would be pretty brief. Essentially, one could easily generalize the setting to learning physical dynamics. Again, the main difference is whether one have quantum memory for entangling information from past and future experiment, and then we can use similar technique to analyze their learning ability. Particularly, we show the following theorem. We show that to uncover whether a unitary dynamic is time reversal symmetric. Note that in quantum mechanics, time reversal symmetry means the unitary only contains real entries. Then what we showed that learning algorithm with quantum memory only requires a constant number of queries, but all learning algorithms without quantum memory will require an exponential number of queries. So to conclude, in this work, we showed that our ability to learn about the physical world can be exponentially improved with quantum technology. That is a combination of quantum sensor, quantum memory, and quantum computer. In particular, the notion of quantum memory plays a key role in the proofs. In a follow-up work, we demonstrate this quantum advantage shown in this work using currently available noisy quantum computer in collaboration with Google Quantum AI. That's it for my talk. Thank you so much for listening.